Now let's talk about winding number. All right, so the winding number before is the number of times a closed curve winds around 0. If this thing here is 0, then given winding anticlockwise, so I claim the winding number of gamma is given by this. 1 over 2 pi I, the integral around gamma of 1 over z dz. Okay, so we're going to show this claim, and the first thing to notice is the following. So proof. First, recall the complex log. Which we define to be this. So log to the base e is just natural log. We just write log to the base e to differentiate it from complex log. So it's natural log of z bar plus I arg. And for the argument, I'm going to take the principal argument. So the principal argument, recall, belongs to pi to minus pi, like this. So we measure the angle like this. This is pi, and like this is minus pi. Right? So for every z, there's a unique number such that this is true, right? So z is equal to e to the I arg of z. This is the principal argument. Yeah? And as you know, this obviously has a discontinuity as we try and cross across the negative real numbers. Yeah? But this, nevertheless, apart from this problem, is a perfectly well-defined holomorphic function, and we can define a different branch which doesn't have this particular discontinuity on this side. So practically speaking, the discontinuity of log usually is not a problem, but it is an essential feature in what we're about to do. So log is the inverse of e to the z. So we have e to the log of z equals z, right? So then if we differentiate it, then we have e by dz of log of z, e to the log of z is just equal to 1, right? And e to the log of z is just z itself, right? So d by dz of log of z is 1 over z. Yeah, just like on the real line, except now it's true as a complex number. So this is what we're going to do. We are going to break this curve up into pieces, and I'm going to make life simpler. I'm just going to make this thing loop around just 2 times. So let me erase some features here. So I'm going to show you that if we loop around 2 times, we're going to get exactly the right thing, and the argument works in general. But we're just going to not write out all the details because it looks somewhat lengthy. Okay, so this is a closed curve. It loops around 2 times. Yeah, and we can start parameterizing it from any point, right? So let's put the negative real numbers here. Okay, and let's start our parameterization just underneath here, and let's go around like this. Actually, let me change colors. So this is the negative real numbers here. So this here is 0. And let me make this in blue. So we're going around like this, like this, like this, like this, like this, like this. So let this thing be the first part of our path. Okay, and I'm going to call that one gamma 1. I'm going to stop just a little bit short of the negative real numbers. And I'm going to restart just a little bit underneath it. I'm going to take this path here, which goes around like this. And does the second loop. And I'm going to call that gamma 2. So that's gamma 2. Better if I had a different color. Let me make a different color. So this is gamma 2 here. And just to stay in the place where it's holomorphic, I'm avoiding the negative real numbers. So I'm just stopping short. So strictly speaking, gamma is not decomposed into gamma 1 and gamma 2. There's also these little bits here that I'm just not going to talk about. So I'm just going to like, there's a little bit here and a little bit here. I'm just going to, well, I'm going to talk about it, but I'm just not going to, I'm going to consider those as errors. So that's the first error, E1. And E2. And they're as small as you like. There are tiny, tiny little bits, just a bit of the path that actually goes through the negative real numbers. So what we have is the decomposition of, so gamma equals gamma 1, union gamma 2, and then these tiny errors. And then E1. And then E2, okay? And we are going to think about this integral right here. So this integral, so integral of our guy gamma one over z is the sum of gamma 1 plus gamma 2 plus these very small errors. Oops. And I don't care about them because 1 over z is bounded because we are some definite distance away from 0. So on this little error here, we are some definite distance away from 0. I'm just going to make the length of this little part as small as I like to make this thing as small as I like. And the same thing here. So these guys, I claim we can just forget about because the function we're integrating is bounded on these little paths, and I can make the length of the path as small as we like. Yeah? So they're not really an issue. So all I really have to think about is gamma 1 and gamma 2. Yeah? So if we look at gamma 1, gamma 1 started here, and it ended here. Yeah? Started here, and it ended here. And let's call the part, the complex number where it starts, a mess. Let's call the complex number where it starts S1, and where it ends is S2. And then gamma 2 starts somewhere here. Let's start where it starts is S3, and where it ends is S4 over here. Right? And S2 and S3 are very close together, and S4 and S1 are very close together. Yeah? And then we can parameterize gamma 1 any way we like, right? But we have the fundamental theorem of calculus in the complex plane. Because for gamma 1, in this region, we have a perfectly nice holomorphic function in an open set. Yeah? Yeah? So we have the antiderivative, right? The antiderivative of this guy is complex log. Yeah? So I know that gamma 1 integral over gamma 1 of 1 over z dz is complex log of the endpoint, which is S2 minus complex log of the start point. And what is this thing? This is log to the base e of absolute value of S1 plus, of S2, sorry, plus the argument of S2 minus log to the base e of the absolute value of S1 plus the argument of S1. That's just the definition of complex log. Yeah? Cool. And for this integral, gamma 2, 1 over z, dz, I have the same kind of thing. Where do I start? I start at S3 and I end at S4. Yeah? So I have that this thing is complex log of S4 minus complex log of S3. And what's that? That is log to the base e of the absolute value of S4 plus the argument, absolute value, plus the argument of S4 minus log to the base e of the absolute value of S3. So I should put a bracket around here. Plus argument of S3. Yeah. Yes, sorry. Yeah, we argument it's got I here. Indeed. Where did I put the original definition? There we go. There we go. Good. All right, cool. So all we have to do is to add this guy to this guy. Yeah? And that, with a tiny error, will give us actually what the entire thing is. Yeah? Yeah? And if we do add these expressions, well, what happens? Well, I claim that the real parts are all going to vanish. So let's see why. Well, vanish with very small errors. So if we add this to this, well, what do we know? We know that the absolute value of S4 is very close to the absolute value of S1. Yeah? So this S4 with this minus S1, these guys will cancel. Yeah? So we're adding these two things. I'm out of space. Maybe I'll put it somewhere, though. Yeah, let me put it somewhere. I just got new pens, but they're harder to erase for my fingers. So, integral of gamma 1, 1 over z dz, plus the integral over gamma 2, 1 over z dz. We are going to have that, again, this guy basically cancels with this guy. There's a tiny error, but we don't care about it. Yeah? And if we look at, let's look at the positive term. If we look at log of S2, log of the absolute value of S2, that's this thing, and that's incredibly close to the absolute value of log of S3, because S2 and S3 are incredibly close together. Yeah? So this guy will cancel with this guy. Cancel in the sense that there's a tiny error. Yeah? So we don't have any real parts except for some very, very small thing, depending on the width of these little things we've jumped over that we don't care about. Yeah? Give me a thumbs up if you're with me. All right, super. So we have just the imaginary parts to think about. Yeah? So we have the I times the argument of S4 plus I, let's put the positive terms, plus the argument of S2 minus I times the argument of S3 minus I times the argument of S1. Right? And then plus or minus very small real error. Okay? But if we look at what these arguments are, so what's the argument of S4? S4, the argument is very close to pi. Yeah? Argument of S2 is very close to pi. Yeah? The argument of S3, we're going around this way, it's very close to minus pi. And the argument of S1, going around this way, is very close to minus pi. Yeah? So this thing is actually equal to 4i times pi plus or minus very small error. So in particular, 1 over 2 pi I, the integral of 1 over z dz, which is very close to this quantity, is basically just 2. And as we let these little gaps get smaller and smaller and smaller, as we have the right to do, then these errors go to 0. Yeah, because all we need is just to have these curves that we've defined be inside an open holomorphic, inside an open set where the function's holomorphic. Yeah, cool. So this shows that breaking up the curve in this way, using the fact that 1 over z is the derivative of log of z, this gives us that this is the correct formula. And this can be generalized to any number of loops just by cutting up into more pieces, as you can imagine. Yeah? Cool. So we do believe this. This thing does indeed give us the winding number. Yeah? Cool. So let me erase the board, and then we will use this to start to describe and motivate the winding number. Sorry, the argument principle. Now let's talk about the argument principle. So oops. So given meromorphic function so when I write meromorphic, it means that it's meromorphic. It means that it's holomorphic except for this discrete collection of poles inside omega. Okay, so I'm not going to write omega take away a bunch of points now. I'm just going to say meromorphic function on omega and understand that to mean that there are poles inside omega where the function is not actually differentiable. And obviously, poles don't have a cluster point in the center, for reasons we discussed. Or not in the center, but inside the set itself. All right, so given a meromorphic function like this and a simple closed curve, C that doesn't intersect any poles, then this thing is equal to the number of zeros inside the interior of C. So number of zeros, counting multiplicity, in so the interior, this means the interior of the simple closed curve minus the number of poles counting multiplicity. Okay, so firstly, let's motivate this. So I'll explain it. All right, suppose we consider what we're going to start by considering what this thing actually means. So suppose we have that z from whatever AB is a parameterization of the curve C, right? Then this quantity is the integral from A to B of f prime of z of t over f of z of t, z prime of t dt, right? And then let g of t be defined to be this, to be f of z of t. Then notice that g of t is a parameterization of the image of the curve C. Parameterization of f of the curve, yeah? So we have some simple closed curve like this, yeah? We parameterize it with z, right? So we are starting somewhere z of a, and it's a closed curve, so z of a is z of b, yeah? We loop around one time, yeah? Simple closed curve. And then this is mapped by f to something, yeah? And then in the image, this thing can do all kinds of stuff, right? Because that's the nature of holomorphic mappings, right? They wrap around themselves easily, yeah? So this could be what happens to the image. But as we go from A to B, then now we are wrapping around like this with our new parameterization, which is wrapping around the image, yeah? So potentially as we go over A to B, we're actually doing many loops around zero. Potentially, yeah? If zero's somewhere here, or if zero was here or here, yeah? So this guy is a parameterization of this, yeah? And then this integral, and we can write star as the integral from A to B of just g prime of t over g of t, because g prime of t is f prime times z prime by the chain rule, yeah? And this thing on the bottom is just g of t, yeah? So then this thing is nothing other than the integral around the image of the closed curve f of c 1 over z dz dz, which is exactly the winding number of the image of C under F. Yeah? So what this thing actually is, it's the winding number of this curve C, it's the winding number of this curve F of C. Yeah? Thumbs up if everybody's with me here. Okay, cool. So let's look at examples. Suppose we have f of z equals z to the n, and suppose we have the curve C is just the boundary of the ball of radius r around 0, whatever radius that is. Yeah? Then what happens to, what is f of c? Then f of c, what is it? Show me with your finger what f of c is. Right, we are wrapping around the circle n times. Yeah? As hopefully you're all very comfortable with now. We just write this in polar form and we see that's exactly what z to the n does. Yeah? Yeah? Cool. So this thing, if we draw it, it's still a circle. Yeah? It's a circle of radius to the n, but it's wrapping around n times. Yeah, it's wrapping around n times. Yeah. So is a circle of radius to the n wrapped around n times. Yeah, so let's see if we believe the statement of the theorem in this case. Well, this is the circle in the domain, this is the circle in the image, and I can't draw it wrapping around n times, but this is, you know what I'm trying to do. And what is the winding number? The winding number is clearly n, right? The winding number of the image of the circle is clearly n. Yeah? Yeah? Thumbs up if you're with me here. Okay. So winding number is now winding of f of c is just n, because we're wrapping around n times. And what's the number of zeros inside the interior of our curve here in the domain? So this is domain, and this here is the image. Well, the number of zeros, counting multiplicity, is n. Yeah, number of zeros, counting multiplicity, is n. So for this particular very simple case, we believe this argument principle. This is clearly true. Yeah? Cool. Let's change the example a little bit. Let's do this. Let's do minus m. Let's do minus m. Yeah? Now, show me with your finger what the image of the circle is under this mapping. What is that? You cut out, but I guess you said this, right? Yeah? And now it's wrapping around clockwise, which means it's wrapping around minus n times. Yeah? It's wrapping around minus n times. Yeah? So it's wrapping around minus n times, because clockwise is the opposite orientation, so minus n times. Yeah? And then let's count the number of zeros and poles inside this thing. Well, the number of poles, counting multiplicity, is m. Oops, it's m, not n. Yeah? The number of poles, counting multiplicity, is m. Yeah? So this thing says that this thing right here, which is the winding number of the image of the curve, yeah, should be minus m, and indeed it is minus m, because we are going round clockwise. So winding number of f of c equals minus m. Yeah? Cool. So in these very simple cases, we get what we want. Okay, let's be more sophisticated. Go ahead. That's the winding number of the image of the curve under f. Yes. The winding number itself of our arbitrary curve is this, right? So given a curve gamma, arbitrary closed curve, the winding number is this thing. Yeah? And what we've learned by change of variables is that this thing here is exactly this thing here. Oh, so what I've forgotten to do is put the 1 over 2 pi I, which might be the point of your question. Okay. Okay. Yeah. So yeah, I want to give this thing some meaning to you. Otherwise, it's just some weird formula. And the meaning of this thing is exactly this, that it is the winding number of the image of the curve under the mapping f. Yeah? And what we're seeing with these examples is that we can easily detect what the winding number of the image of the curve is in these simple examples, because we can just track what's happening, right? And it's conforming to this theorem that whatever the winding number of the image of the curve is, that is given by this thing, the number of zeros minus the number of poles. For these two simple examples, we've taken z to the m or z to the minus m. Everybody together. Cool. All right, let's get fancy. Let's take a example like this. What if we have f of z is equal to z to the n times z minus I to the minus m. Yeah? So let's take some circle with a large radius. Right? Tell me roughly what's happening to the circle when we map it with respect to this f here. What's happening to this circle? What's happening to it? Take the radius to be very big to make things simpler for yourself. What's happening to it? Come on. Well, if I just had z to the n and then z to the minus m, you could answer that question, right? Because that would be just z to the n minus m, which is one of these cases, yeah? So if we're out very, very large scale, yeah, then for z which is very large, it doesn't really notice this minus I very much, right? Yeah? So that function for very large z is a lot like just z to the n minus m. Yeah? Yeah? So for very large z, you would expect this to actually be either taking the circle and winding it round. Well, depends where the m and n, what the signs of them are, right? So I'm going to say it's going to wind around n minus m times, where by that I mean n minus m is the number of clockwise times it winds around. Yeah, that's what we expect for very large radii. Yeah, because it's morally just like z to the n minus m. Yeah. Cool. So that implicitly takes care of the case when n is less than m. And when I say it winds around n minus m times, I mean it's winding around clockwise. Yeah? Yeah? Cool. All right. So let's see if we have a large radii, if we actually believe this theorem. Well, I hope we do, right? Because if we have a large radii, then 0 is here and I is very, very close by. Yeah. And what's the number of zeros we have? We have n zeros. And what's the number of poles we have? We have m poles. Yeah. So again, the winding number is indeed n minus m. Yeah. And we can see that hopefully somewhat naturally when we take large R, because then we know that this behavior is an awful lot like, again, z to the n minus m. But this theorem holds true for any R, so long as we actually have radius bigger than 1, and we don't actually cut out this complex number I. This is actually also true for anything like this, for any radius bigger than 1. Yeah? And you can kind of have a kind of a plausibility argument that if it's true for all large radii, yeah, and then since this thing is some sort of an integer, right, and it's going to probably change continuously, if it's true for all large radii, then it's going to be true until something dramatically changes, like we go through a singularity. Yeah, because everything will be continuous when we're away from the zeros or the poles. Yeah. So hopefully this seems reasonable even for any radius. Yeah? Any radius that includes both 0 and I. Cool. So what does this say? This says that the influence, the topological influence of zeros or poles is indestructible. That if you have some function which has some zeros here, then that is forcing your your complex function to take the complex plane and wrap it around each one of these zeros. And if you have a bunch of poles around here, then that is forcing the complex function to take the entire complex planes and wrap it around clockwise around these poles. So if you have something that contains these guys here, then the wrapping around that occurs is entirely forced by these zeros and poles, and nothing gets lost. The only way you have any cancellation is when you have clockwise wrapping around being cancelled by anti-clockwise. Yeah? So it means that topology is indestructible for holomorphic functions. You can't do any crazy thing and then have some sort of wrapping around. I mean, we have these things locally. We know these things on a very small scale wrap around how we think, right? Because we know when we have a zero that f of z is equal to z minus z0 to the n times some nice holomorphic function, which is non-zero around z0, yeah? So locally, it's wrapping around in a nice way, yeah? So if we have a zero. And we also know that if we have a pole, f of z equals z minus z1 to the minus m, and then h of z for another holomorphic function, which is non-zero at z1. We have some clockwise wrapping around in this case, yeah, locally, just because these representations hold true locally, yeah. But what this says is that the wrapping around you see locally has to sort of keep going forever, goes on forever. There's no way that it just like, there's no way that it just kind of like just diffuses out. The wrapping around is a topological property that can't be undone by a holomorphic function, except by some wrapping in the opposite direction. That's what this theorem says. Yeah. So it's kind of remarkably strong theorem. So when you have zeros and poles, they force a topological behavior on your holomorphic mapping that perpetuates forever. Yeah? Sort of just goes on forever outwards. Yeah, so, yeah. I mean, you might think that that's natural, and you know, most examples you can think of things wrapping around do something like this, but actually being able to prove such a definitive statement is kind of surprising. Normally, it's very hard to prove. It's normally very hard to prove things that seem naturally topologically to be true. Often it's an incredible challenge to actually demonstrate it, but not in this case. As I'm about to show you, the proof of this is very simple. It's very simple. Okay, so everybody happy with what this thing says? Yeah, makes sense? Cool. Proof. All right, so suppose f has a zero at, say, z0. Then, as we know well, f of z is locally representable like this. To the n, g of z, where g is holomorphic, and g of z0 is not equal to 0. Yeah? Then let's see what happens when we just differentiate this. If we differentiate this, we're going to have n z minus z0 to the n minus 1, g of z plus z minus z0 to the n, g prime of z. Like this, right? So then if we consider this quantity, f prime of z over f of z, locally around this z0, then what happens? So we're just going to take this expression and divide this expression right here. And what we're going to have n over z minus z0, yeah? Taking this thing and dividing by this thing. And then here, we're just going to have plus g prime of z over g of z. Yeah? And G prime is holomorphic, G is holomorphic and non-zero around Z0. So in a small neighborhood around Z0, this thing is representable by this. Yeah? So holds true in, say, B R of Z0 for some small bigger than 0. Yeah? So in particular, it says that f prime over f has a pole at Z0, yeah? And the residue of the pole is just given by n. Yeah? It's got a simple pole, and the residue is given by n. So residue of f prime over f at Z0 is just equal to n. Yeah? Cool. Now suppose f has a pole at Z1. Then, same kind of game. We have that f of z equals z minus Z1 to the, say, minus m h of z, where h is holomorphic, and h of z is not equal to 0. I should say that this is all local. Locally, write that better. Locally around Z0. Yeah. So same going. They have this or this, and this holds locally around Z1. Oops, it's Z1 now, not Z0. It's not equal to 0 locally around Z1. And then we do the same thing. We're going to differentiate this guy. F prime of z, we have minus m, z minus Z1, so the minus m minus 1, h of z plus z minus Z1, minus m, h prime of z. And then when we consider this quotient, f prime of z over f of z, then using this representation and dividing through by this, like this, we're going to have minus m z minus Z1, yeah, like this. And for this thing, all we're going to have is just h prime over h, right? And again, since h of Z1 is non-zero, this part's perfectly nice. We have nothing going on except a pole of order 1, a simple pole at Z1, and residue at Z1 of f prime over f is equal to minus m. Yeah? Cool. So the only place we have anything happening with this expression here will be when we have either poles or zeros. Outside of poles or zeros, then this thing will be perfectly nice, analytic. There'll be no problems with it. There'll be no issues with it. You know, just because by the quotient rule, if we're not near a pole or a zero, then we're differentiable and everything's good. Yeah? So by the residue theorem, we can just calculate the integral of f prime over f, residue theorem. Yeah. If we integrate this thing, f prime over f dz, then this is just 2 pi I times the sum of the poles, right? So zk, the residue at zk of f prime over f. Yeah? And then this is just nothing but 2 pi I times number of, so no dot is number of zeros minus number of poles. And that's it. Yeah? Remarkably easy to prove. It's just an application of the residue theorem. Yeah? Cool. All right, so this strong theorem is very simple to prove. It's very simple to prove. All right, cool. And this has many, many consequences. And let me see if I can fit the next one in. So one of the consequences is Roche's theorem. How are we for time? We're okay. Okay. Suppose we have F and G holomorphic on omega, and C is a simple closed curve that doesn't go through any zeros of F. And suppose that the absolute value of F is strictly bigger than the absolute value of G on the curve C, then the number of zeros of F plus G in the interior of the curve equals number of zeros of F in the interior. Okay, so we have some sort of domain like this, and we have a closed curve that doesn't hit any of the zeros of F. It can be some outside, but the closed curve messes them like this. Okay. And we have two functions, F and G, holomorphic on omega. And we're going to consider this thing, F plus G. And we're going to think of this, well, the way to think of this is a kind of perturbation of F. Okay. It's a perturbation of F. Yeah. But it's a perturbation such that G is always less than the absolute value of G is always less than the absolute value of F. Then the claim is that if we change F by adding G, it's not going to change the number of zeros. That's the claim. Okay, so I have set up a demonstration of this. Now, as we've learned, the number of zeros of inside the interior of C is given by the amount of times that F of C winds around zero. Yeah, that's the argument principle that we just learned. Yeah. So if we knew that the number of times that F winds around zero, let me start again. The number of times that F of C winds around zero is the same as the number of times as F plus G winds around zero, then this is automatically true. Yeah, because that's the argument principle again. The number of times the image of C under F winds around zero is the number of zeros inside the interior. Yeah? And the number of times f plus g winds around the image of c under f plus g winds around 0 is the number of zeros of f plus g. Yeah? Yeah? So if we consider this f plus g, and it winds around, and the image of the curve winds around the same number of times as f, then we're all set. Is that making sense, people? Yeah? Give me a thumbs up if so. Cool. All right. So we're going to make life simple, and we're going to think of f as winding around 0 in this very simple way like this. So forget about this timing. So this is f winding around 0. This is f winding around 0, like this. This is f winding around 0, okay? And 0 here is in the center. Yeah? And then this thing here is f plus g. This thing is f plus g. And the only restriction is that absolute value of f is always strictly bigger than the absolute value of g, right? So this thing is the absolute value of f, right? So this is 0, and this is g, right? And g could be pointing anywhere, but the absolute value of g is always less than the absolute value of f, right? Yeah. So look, so watch what happens as g is doing whatever it wants to do. Like g is going round like this, perhaps. It's going round, like doing this maybe. G could be doing all kinds of weird stuff, going round, circling around, doing whatever it wants, right? But as f is going around 0, then because g is restricted in the way it is, that its absolute value is always less than f, right? No matter what it does, it's forced to go around the same number of times as f itself. Yeah? No matter how crazy g wants to be, if f decides it wants to wrap around twice, right? No matter what g does, it's forced to wrap around twice as well. Start that again. If f wants to wrap around twice, no matter what g does, then f plus g must wrap around twice as well. Do you see what I mean? Yeah? So look, if we start here, then no matter how much g doesn't want to wrap around, no matter how much it resists, it's forced to wrap around as well. Yeah? Is that making sense? Give me a thumbs up if so. Sanka, you okay? Cool. So, our hypothesis that f is bigger than g is exactly the fact that this line, or this piece of string, is longer than this piece of string. Yeah? So the wrapping around of f is forcing the wraparound of f plus g by the same amount. Yeah? By the same amount. So geometrically speaking, we would expect this to be true. We would expect this to be true. We would expect it to be the case that if we consider how much wrapping around f plus g does, it should be the same amount of f. Yeah? Just by visualizing what this hypothesis implies. Yeah? And then by the argument principle, that says that we should have that the number of zeros inside of the interior of C for this function f plus g should be the same as the number of zeros of f. So this statement seems a little bit technical when you first see it, but visualizing it as g being trapped into doing whatever f wants to do, I think kind of makes it somewhat clearer, right? And this is a simplification because I'm just taking f to have like this constant absolute value here. But if I had, you can imagine that if I had a more sophisticated model, the same thing would still be true, right? So long as this is always true, then whatever wrapping around f does, then f plus g must do the same wrapping around. Yeah? Cool. All right. So intuitively, geometrically, we believe this. We believe this. It seems to be true. But we want to prove it. We want to make sure this is what math does. We have our intuition, we have our proof. So, define the following: f of t of z to be equal to f of z plus t times g of z. Okay? So f of 0 of z is just f of z, and f of 1 of z is f of z plus g of z. Yeah? Then let n of t be the number of zeros of f of t inside a curve C, like this. Yeah? Now, claim if n of t is continuous, then theorem is proved. I'll prove it. Because if it's continuous, then whatever we are at 0, we have to be at 1, right? So if we have a continuous function into the integers, then it has to be constant, because if it's not, then we have a discontinuity. Yeah? Yeah? And it's proven, because if this number changes, if n of t changes, is not constant, then we have a discontinuity. Okay, so it's enough to show that this n of t, the number of zeros of f of t, is continuous. Yeah? 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 But n of t is nothing but the integral 1 over 2 pi I integral around the curve of ft prime over f of t dt, dz, sorry. Because that's the previous theorem, that's the argument principle. Yeah, that's what we've learned. And I claim that this thing is a nicely continuous thing. This is a nicely continuous thing. Okay? All right, so suppose we have some sequence tk tends to t tilde. It's enough to show that the limit as k goes to infinity of n of tk is equal to n of t tilde. Yeah, that would be enough. That's exactly what continuity is. Yeah? Well, let's look at these expressions. So look at this. So n of tk minus n of t tilde, what is it? It is 1 over 2 pi I, the integral of c of f of tk prime over f of tk minus f of t tilde prime over f of t tilde, right? Like this, yeah? And we can clean that expression up by having a common denominator, like this. And then we're going to have f of t, f of tk prime times f of t tilde minus f of t tilde minus f of tk over this thing. Oops, the product. Yeah? Everybody happy with this? Yeah? And what we'd like to do is to show that this stuff in here uniformly goes to 0 for all z on the curve, yeah, as we let k go towards infinity. That's what we'd like to do. And let's identify what can go wrong. Well, when we see a quotient expression, one of the things can go wrong is if the denominator blows up. No? But the denominator is not going to blow up. The denominator is not going to blow up because we've set it up so that f has no zeros on the curve itself, and that g absolute value is less than f on the curve. Yeah? And this thing is just a linear combination, not a linear combination, it's just f plus t times g, where t is between 0 and 1. And since g absolute value is less than f absolute value on the curve, then this thing can't mess it up with this thing. So the absolute value of f subscript t is always bigger than 0 on the entire curve. Yeah? Yeah? And in fact, it's bigger than some constant independent of t itself. So notice that absolute value of f of t of z is bigger than equal to the absolute value of f of z minus g of z, like this. Yeah? And this thing, by definition, by hypothesis, I should say, is always bigger than 0, and it's a continuous thing, and it's in a closed set, so this is actually bigger than some small delta for all z on the curve C. Yeah? So these guys on the bottom are never going to be a problem for us. They're not blowing up. Their absolute value is always bigger than delta squared, the product of them. Yeah? Okay, so these guys are not dangerous for us. Yeah? Then we have to look at this thing. Well, we have this k thing here, and then this t thing here, and these expressions are different. And the natural way to deal with this is to break it up into two differences where the guy we put in the middle shares one element of each. So what I mean is, if we look at this expression here, so f prime of tk, f of t tilde minus f prime of t tilde, f of tk, we want to consider something like this: f prime of tk, f of t tilde, and let us do this. Let's write f prime of t tilde, f of t tilde, and then let's write plus f prime of t tilde, f of t tilde. So we'll have plus minus, we'll kill these guys, and then minus this thing, f prime of t tilde, f of tk, like this. Yeah, and then we consider, this is a standard trick we do a lot. So we consider this difference and then this difference, and then we'll factor out the common part of each one of these separate differences. So we'll factor out the f tilde from the first thing. So f tilde, like this, f prime of tk minus f prime of t tilde, like this. Yeah, and then we'll factor out the f prime of t tilde, like this, f of t tilde, f minus f of tk. Yeah, Cool. And then if we look at this, then these guys are tending to 0. Just by the way we set this up, right? If we take the derivative of this thing, yeah, then as tk goes to t, then f prime of tk plus g prime is going to tend to f prime of t tilde plus g prime, yeah? So this thing goes to 0, and this thing also goes to 0, yeah? And this can be made uniform in terms of z because of the nature of these expressions, right? Let me put some more details. So look at this. So f of t tilde minus f of tk, just how we got these definitions over there. Then what's this thing? This is less than, so the f's will just cancel. It's just less than t minus t tilde minus t times g of z. G is a holomorphic function on this closed curve, so therefore it's bounded on this closed curve, so we can make this thing as small as we like, independent of z. Do you see what I mean? Yeah? And if we look at this expression here, f t tilde prime minus f prime of tk, it's almost the same thing, so we differentiate and then we'll have the cancels of the f prime and we'll have this thing here. t tilde minus tk, g prime of z, and again g is holomorphic, g prime is holomorphic on the closed curve, and we have no problems. This is bounded independent of z. Yeah? Cool. So, if we take absolute value signs around this thing, so then we have less than and equal to, absolute value around this, absolute value around this, and then absolute value around this, absolute value around this, which is the same as absolute value this times this, this times this. And we have that these guys here are tending to 0 as tk goes to t tilde, independent of z. So the stuff on the numerator is definitely going to 0 uniformly with respect to z around the curve. Yeah? So the numerator is definitely going to 0 uniformly, and the denominator is definitely bounded above. So this stuff inside the integral is uniformly converging to 0. So we can pass the limit through the integral and therefore have that this thing in the limit is equal to 0. Yeah? Everybody happy? Thumbs up if you're happy. Cool. All right, so the integrand, which is the thing inside the integral, over the curve C, so we can pass the limit we do indeed have that the limit as k goes to infinity of n tk is equal to n t tilde, and we have continuity, and that's all we need. Yeah? So this function, n of t, is a continuous function. Yeah? Into the integers, therefore it's constant, and therefore the number of zeros of f is the same as the number of zeros of f0, because that's by definition, which is the same as the number of zeros of f1 by continuity, which is the same as the number of zeros of f plus g. And that proves the theorem. Yeah? Cool. That proves the theorem. Yeah, the next theorem is that the image of an open mapping is open. And yeah, it's probably better not to try and squeeze that in into 10 minutes. Thank you for accommodating me in this strange time. Jamie, I think we're about to start grading for the next couple of hours. The rest of you, I will see you next week. All right, have a good day.